Hey, I'm Jared.
I'm Matt.
I'm Aaron.
I'm Mark.
And I'm Alex.
And our project today is to help preserve the structural integrity of your gingerbread house. For our project, we decided to examine a gingerbread house to see how it could fail. We determined that the gingerbread house would have two possible modes of failure. These possibilities would be in the adhesion, which is the icing, or the gingerbread itself. To simplify the construction, we decided to build a ginger bridge. The ginger bridge was chosen not only because it was simple for construction, but it was also much easier to visualize which aspect of the assembly would fail first.
Hi, this is our ginger bridge. We use the ginger bridge because it's a lot easier to test and see where it will fail than a gingerbread house. Our ginger bridge is made out of gingerbread and these three beams and held together with frosting in between those areas. Now, to test it, we took some weights and put it right here in the middle of the bridge. And there are three main ways that this bridge will fail. The first two are given with normal stresses, where sigma is equal to mc over I, with m being the force of our weights times the distance from the support, c being our distance from the central axis of the middle beam, and I being the moment of inertia. Now, the first way it can fail is that the frosting tears apart because of the normal stresses generated along this area. And in the second way, the gingerbread will fail because there's also normal stresses at the very bottom of this beam, and since it is a brittle material, it will fail in tension at the very bottom here. Now, the last way it can fail is through shear forces, with the supporting beam sliding past the central beam, and that's just tau is equal to V over A, with this V being a shear force created by our downward weight force, and A being the frosting contact area. And these are the three ways that we think this ginger bridge will fail.
As you can see in this CAD simulation, the areas in red are experiencing high, normal, and shear stresses. To predict where the bridge would fail, we isolated these sections and tested them individually.
First, we attempted to find the shear stress failure, but the normal stress due to the moment caused it to fail prematurely. This indicates that tensile stress of the icing is weaker than the max shear stress. As you can see, the moment causes the piece under the load to peel away from the support at 760 grams. Next, we tested the normal stresses by simply supporting the gingerbread and applying a load to the center. This section failed in tension at 700 grams.
Applying the knowledge from our preliminary testing and the equations explained earlier, we predicted that the supports with the icing would fail first. This prediction was made because not only would the moment be larger in this scenario, but also the moment of inertia would be smaller, leading to a higher stress on the supports. The supports ended up failing at a load of 500 grams. While we were correct in predicting that the supports would fail first, the model failed in shear stress as opposed to normal stress.
While we know that the icing failed due to shear stress, it still took a weight roughly equivalent to 156 gumdrops to cause it to fail. With that in mind, hopefully, this presentation will help you keep your holidays safe this winter.